Welcome to this explainer. Today, we are taking a totally mind-bending journey from the microscopic atoms powering our devices all the way out to the planetary impacts of our digital world. We're going to explore the incredible science of electronic materials, how they're actually made, and the massive hidden footprint they leave behind. So let's just dive right in and ask ourselves, what kind of invisible magic is actually happening beneath our screens to make modern life possible? When you hold a smartphone or a laptop, you're holding literally billions of microscopic components, exotic metals, and highly engineered materials. But what are they exactly, and how do they work together? To really wrap our heads around this, here's our roadmap for today. First, the magic of semiconductors. Second, sculpting the silicon microchip. Third, rare earths and heat management. Fourth, the hidden environmental toll. And finally, closing the e-waste loop. All right, let's kick things off with Section 1, the magic of semiconductors. Now, the crazy thing about semiconductors, like silicon, is that they sit perfectly right between pure conductors, like the copper wire in your walls, and insulators, like the glass in your windows. In its pure state, a silicon crystal isn't actually very useful because its valence bands are filled up, preventing the flow of electrons. But thanks to its unique quantum band structure, we can precisely manipulate it to control the flow of electricity. But here's the catch. To make that silicon actually work for computing, we have to do this incredibly precise chemical process called doping. And this drastically alters how electrons behave in the material. By introducing highly controlled amounts of impurities, we can change silicon's electrical conductivity by orders of magnitude, essentially turning it into a dynamic microscopic switch. So how do we do this? Well, we do it in two main ways. If you add an element like phosphorus, you get N-type silicon, which has extra negatively charged electrons. On the flip side, adding boron creates P-type silicon, which has these electron holes that act as positive charges. By snapping P-type and N-type silicon together like puzzle pieces, we create a P-N junction. And that right there gives us the transistors and diodes that act as the fundamental digital switches for literally all of our devices. Moving right along, let's jump into Section 2, sculpting the silicon microchip. Actually building one of these chips is a massive feat of engineering. It's a highly complex, sequential process. We start by taking a pure silicon ingot and slicing it into wafer-thin sheets. Next comes photolithography, where we use ultraviolet light and custom masks to carve incredibly intricate patterns. Then comes that doping process to create the transistors, and finally, we wire the whole thing together. You can really think of a microchip as a bustling, microscopic city. The billions of transistors, those are your buildings. And the copper interconnects, they're the super efficient highway systems letting all that electron traffic zoom around. Back in the late 90s, the industry shifted from using aluminum wiring to copper, and that fundamentally changed how fast our computers could actually run. See, copper conducts electricity way better than aluminum, which reduces resistance and drastically speeds up the chip. But it has one fatal flaw. It diffuses straight into silicon and completely destroys it. Engineers cleverly solved this by lining the microscopic trenches with a barrier metal, like tantalum, before filling them up with copper using this amazing bottom-up electroplating process. Which brings us to Section 3, rare earths and heat management. Beyond just silicon and copper, it's honestly amazing how specific rare earth metals are absolutely non-negotiable for modern tech. Take europium and terbium, for example. Without those two, your screens would completely lose all their vivid red and green colors. Meanwhile, neodymium gives us the tiny, super powerful magnets in our speakers, and dysprosium ensures they don't fail when your device gets really hot. And speaking of heat, because these tiny components are crunching billions of operations every single second, they generate massive amounts of it. To manage this, engineers use advanced dielectrics to insulate circuits. They also rely on thermal interface materials, or TIMs, to actively pull heat away from the chip itself. Some cutting-edge solutions even use aligned carbon nanotubes or low melting point alloys like bismuth, just to keep your phone from literally melting right in your hand. Now, we need to zoom way out for Section 4, the hidden environmental toll. Let's put this into perspective with a pretty wild statistic. It takes roughly 10 times the weight of a 53-pound computer setup in fossil fuels just to manufacture the thing. So that is over 530 pounds of fossil fuels, plus an astounding 3,300 pounds of water just for one single desktop computer. Getting all those raw materials out of the ground has massive global impacts. Remember tantalum, that crucial barrier metal for our copper interconnects? It's often extracted from an ore called coltan. Now, Sources report that significant coltan mining occurs in the Democratic Republic of Congo, where this highly complex supply chain has sometimes been linked to the financing of civil conflict. It really illustrates the deep, real-world consequences tied directly to our electronic components. And we just churn through these devices at an astonishing rate. Get this, a staggering 26 to 37 million computers became completely obsolete in the US in the year 2005 alone. And today, the average lifespan of our electronics has only continued to shrink. Because we replaced our gears so fast, millions of tons of e-waste end up sitting in landfills or getting shipped overseas. And discarding electronics isn't just about throwing away bulky plastic. It risks exposing the environment and often unprotected workers to highly hazardous materials like lead, cadmium, and mercury. But there is some good news here, which we'll cover in Section 5, Closing the E-Waste Loop. You might not believe this, but 1 single metric ton of recycled circuit boards can contain 40 to 800 times the concentration of gold found in a ton of actual mined gold ore in the US. Our old electronics are essentially high-grade urban mines, just packed with precious metals waiting to be recovered. By recycling, we actively mine our old devices for copper, aluminum, lithium, cobalt, and those rare earths we talked about. This keeps these precious materials in a circular economy, it stops toxic heavy metals from leaking into the soil, and it drastically cuts down on the energy-intensive, highly destructive process of mining for virgin materials. If you ever wonder if tossing your phone in an e-waste bin actually matters, well, here's a clear reminder. Responsible recycling isn't just about reducing trash, it's about massive resource conservation. In fact, properly recycling just 1 million laptops saves the equivalent electricity used by 3,657 homes in an entire year. So, from the microscopic precision of doped silicon to the very real planetary impact of global mining and e-waste, our digital lives are built on some incredibly complex physical materials. It's a lot to think about, right? Now that you know the incredible science and the true cost behind your screen, what are you going to do with your next obsolete device? Thanks so much for joining me for this explainer, and keep exploring the amazing world of materials around you.